Hi, so I'm Andy Weir, work with special projects. I'm just going to start off with a disclaimer that it's been a while since I've done any electronics in anger, so take everything I say with a pinch of salt, and if someone on the internet says something that's different to what I do, it's probably right. The other one, safety. Electricity can kill, so make sure you work safely. I'm not going to tell you what the safe voltages are, that's down for you guys to look after yourselves, but sort of Arduinos and Raspberry Pis are generally safe. But I just wanted to mention that so people don't sue me for electrocuting themselves. So we're going to start off with a quick introduction. Oh, shut up. Then we're going to look at electrics first. Basic concepts. Electronics is basically physics and maths. So we're going to look at sort of some of that, some terminology and some concepts. Going to look at some of the fundamentals. You have to learn to walk before you can run. So before we start messing around with Arduinos and Raspberry Pis, we're going to look at sort of some of the basic understanding of electric circuits. And going to do a quick summary. And it says a quick break there, but we're not allowed to have a fag break, so we'll go straight through. And then I'm going to move on to electronics, and I'll sort of discuss the difference between electrics and electronics when we get there. So I'm going to look at power and signal. Going to look at a control loop. And then we'll have a quick summary. So sort of, it doesn't look like much, there's quite a lot there. It's sort of 5, 10 years worth of electronics condensed down into 40 minutes, so it's not going to be comprehensive. So in a past life, I used to fix these things. And what's interesting about this and relevant is you watch as it goes around a bend, the gun fixes on a point in space, and as it goes around a bend and up and down the hill, that gun stays fixed in space, and that's using electronics, measurements, sensors, and control loops to achieve that. So that turret there is about 20 tons. So there's a lot of beefy stuff going on there to control that. And for the petrol heads or diesel heads, it's a Rolls-Royce designed Perkins Condor CV12 engine. Twin turbo, generates 1,200 brake horsepower, which is a lot, but then it's got to generate a lot of power. So that's one of my past lives. Oh, stop. In another past life,
we were 70 degrees north in the Barents Sea.
I was involved with this project.
Sea ice found north of Alaska. Down there, 300 meters below, we find Snow Beach, the world's northernmost offshore gas field. Opened in 2007, the field was the first development in the Barents Sea and the first pure subsea development on the Norwegian continental shelf. Every day, 17,000 standard cubic meters of wet gas carry out a 143-kilometer journey through the pipeline, ending at the Medvay LNG plant on the northern coast of Norway.
So that's offshore, not like a traditional oil well where you've got a rig on top and people that sort of control the operation there. It's offshore, automatic or remotely controlled. And the piece of the puzzle I was involved with, there was a safety shut-off valve above the wellhead. So there's two valves and 3 sensors, and it was a voting system that voted whether the pressure was too much, whether to close down the wellhead so it didn't blow up the pipes, because it's a long way up. 143 kilometres to go and fix a pipe. So in my current life, I've done things like made a valve amp, wireless home sound system, a bit like a Sonos, but not as pretty or expensive. Sumo robot. Christmas tree lights were in the SVD office over the road when we had those, sort of flashing and dancing. Quadcopter, we'll see more of that later. Most of my PCs I've built myself. I don't think I've not built one. Not exactly electronics, but programmed a Pebble watch to do a sailing race timer. And again, this is electrics, but rewired my house. So those skills that I learned when I was fixing tanks or when I was designing and developing electronics for the oil and gas industry, cross over. It's the same things. It's basically we're either measuring things, or we're controlling things, or we're communicating. And that's pretty much it. So we'll look at some electrics first, and the basic concepts. So we've got another video. Made it challenging. So we've got Newton's cradle there, and the ball comes down, and then some energy is transmitted along those balls, and the ball goes up. It must be transmitted, because otherwise the ball doesn't go up by itself. It comes back down, energy transmitted, and the ball goes up. So there's energy being transmitted there, but the balls in the middle don't really move. And that's similar to an electric circuit. So if you imagine you had a tube full of marbles, and you sort of shove a marble in one end, you'd get a marble out the other end. And if you just put 2 marbles in one end, you get 2 marbles out. 5 marbles in, 5 marbles out. And if you shove them in really hard, you get 5 marbles out the other end really fast. So there's energy flowing down that tube, but the individual marbles or electrons and electricity, the individual electrons don't move very far. So that's the electrical circuit, and that's the electrons moving down the conductor. So we've got a tube for our marbles, and we've got a piece of metallic wire for our electrons. Another important thing is if we broke our tube, we wouldn't get marbles out the end here. We put them in, and they'd sort of drop down the middle. And if we break our electric circuit, we won't get electrons out the end. So that's an open circuit, so that's sort of worth bearing in mind. And then, if we got really creative and got a hula hoop and filled it full of marbles, and we put some energy into that hula hoop to start the marbles moving around, so long as we kept on injecting more energy in to compensate for the energy we've lost through friction and moving the marbles around, that would keep on going. That's the same with an electric circuit, so we can keep electrons moving round and round in an electric circuit, providing we keep on injecting energy in to compensate for the energy coming out again. So it's a flow of energy. So when we talk about flow with electronics, electrics, it's a flow of energy, and that energy is transmitted by electrons. So we've got another concept, voltage. So we imagine here, probably can't read it very well, but on the left-hand side, we've got a pump. On the right-hand side, the water's falling back down. So we pump water up out of a reservoir, put it in the tank at the top, and then let it fall down again. So we're injecting energy into the system when we pump the water up. We're storing it at the top, and then we're releasing it down to the bottom. So it's storing energy and releasing energy. So that's voltage. And if we make the tank higher up, we can store more energy. But that's qualified. So I've got a prop here, and I've just stored some energy in my box here. And if I release the energy, you've got sound waves and noise and things. If I held it here, is that going to be more or less energy than a second ago? Less. Yeah, less. Not quite so loud, or it landed better. What about if I stood on top of Mount Everest and held it up there, more or less? How about if I only dropped it to my feet on top of Mount Everest? Same. Yeah, so that's the point I wanted to make. The sort of the amount of energy stored is relative to somewhere. So we've got potential energy from physics, and we've got a drop. And those are 2 terms we use in electronics to describe voltage. So the parallels there. And voltage, we measure the energy between 2 points. So moving on to fundamentals, this is where we get a load of beardy white men with too much money and too much time started thinking about electronics in the 18th century. So they come up with all sorts of things that they said. So we start off with George Ohm, who said the current through a conductor between its 2 points is directly proportional to the voltage across the 2 points. So if we look at that, that's Ohm's law. I don't know if you can read that. We've got three variables there. We've got voltage or electromotive force. We've got current, symbol I, and we've got resistance, which is in ohms. So you've got his name, mid-world famous. So if we look at the 2 points across the light there, the voltage across is dependent, and the current through are proportional to each other, depending on the resistance of the bits in the middle. And we can jiggle all those equations around, and we end up with a triangle. So long as we know two of those three things. If we know voltage and current, we can work out the resistance. If we know resistance and voltage, we can work out current. If we know current and voltage, we can work out the other one.
Why is it not U?
U?
Instead of E?
It can be E or V. So it's either volts or electromotive force. And you'll see in a second why I prefer to use E. It's just convenient for the next one. Is it different in Germany?
It's U.
Well, what the Germans say? It's not so. Your German's German. Maybe it's a V. German V. Yeah. I don't know. But in English, is it a V or a E?
Is electron flow different from current flow? Because generally
Sorry?
Is electron flow different from current flow? Because generally I have studied from positive to negative it flows.
Yes, the people in the 18th century didn't actually know which way electrons flowed, so they made a guess and they flipped the coin and came up wrong. So what's called conventional flow, positive to negative, is what we see on sort of diagrams and described in circuits and books. But real electron flow actually flows from negative to positive. But once everybody had learnt it was too late, 100 years or so. So then we have James Prescott Joule, and he came up with one of his laws. The power of heating generated by an electric conductor, so imagine some current going through, is a product of its resistance and the square of current. So we've got power, we've got current, and we've got electromotive force again, volts. P equals I squared R. I squared R normally means that you're releasing smoke from your circuit because it's manifesting itself in heat. So that's how energy escapes from an electronic circuit generally. It can escape in other forms, but it's generally in heat. So again, we can jiggle these round, and eventually we come up with another one of these triangles where if you cover up P and you know I and E, you can calculate it if you cover up I, P and E, and the other one. And that's why I use E, because then you remember the power one is pi. Even though it's a triangle of pi, it's still a big apple pie. So just to sort of illustrate power, we've got some resistors here. They're different values, but they don't look very much different if they're the same values. You probably just pass them around as a box at the end. I've got more props, just if you want to see those. So the big fat ones for high power, little skinny ones, because there's not much heat generated, they don't need to cope with much, so they're low power ones. So we got another beardy 18th century bloke called Gustav Kirchhoff, and he came up with a couple of laws. He got mentioned twice. So the directional sum of the electrical potential differences voltage around a closed network is always zero. So we've got a circuit there. Basically what it's saying is if you put an electric meter at the top of those two resistors there and an electric meter down the bottom of those resistors there, and measure how much was there, say it was 10 volts, and then you measured across one, say that was 5 volts, and you measured across the other one, you'd be expecting 5 volts. So the total sum of the voltages add up. And the current flowing through is the same through both resistors. Whatever impact those resistors have on the current flow will always be the same, 5 marbles in, 5 marbles out. We have another one from Kirchhoff. At any node or a junction in an electrical circuit, the sum of the currents flowing into the node is equal to the sum of the currents flowing out of that node. So what that means is if we've got a circuit like this, and if you had a current measurer, there is such a thing as a current measurer, but they're not very general. They measure the current going into the top dot, and say that was 1 amp, and you measured the two currents going down, say that was half an amp and half an amp. That's how you expect it to be, that what comes in goes out, which makes sense, because if you put 5 marbles in, you get 5 marbles out. So that's sort of a bunch of 18th century people. I'm not going to sort of dwell on it too much. You go and look those up if you need to, but they're there. So now we're going to do something a bit more practical. This here is like the hello world of robotics, the Arduino blink circuit. So you've got a light and you've got a resistor, and you write some code and you make the light blink on and off. But the resistor is what we're interested in. It's called a current limiting resistor because we know I squared R makes heat, which makes the magic blue smoke escape from our circuits, which we don't want. And you probably don't need a resistor on an Arduino, the same as you probably don't need to unit test if you write your code properly, and you don't need to refactor if you do it right the first time. But you end up with tech debt in software, and you might get it okay with an Arduino, but if you get some expensive piece of equipment and just go sticking LEDs on willy-nilly, you might end up with the blue smoke being released from your expensive circuit board. So we'll have a quick look at this. So we've got that there drawn again as a circuit. And we can know something about our LED. You probably can't read that, so I'll try and describe it as best I can. So if we look in the documents for our LEDs, we go to Maplin or somewhere, in fact not for very much longer actually, is it? We go to Maplin, get an LED, and look at the documentation for that. We'll look online for the documentation. Standard 5mm LED has a max current of 20 milliamps and a forward voltage drop of 2 volts. What that means is the diodes and silicon in general doesn't change its voltage. It has a fixed amount of voltage that you appear to cross it, so everything else has to move in response to that. So we also know about an Arduino, the voltage output is 5 volts. So we've got some laws there. We've got Ohm's law and Kirchhoff's voltage law that we can use. So if we know we've got 2 volts at the top and we've got 5 volts overall, 3 volts at the bottom. So we can then define the current. It's I equals E over R. So we know we've got 3 volts over R, jiggle it around, R equals I times E. And that gives us 150 ohms, which you probably can't read that unless you've got pretty good eyesight. So we've basically used our 2 beardy 18th century gentlemen knowledge to work out that. Next, Joule's first law. We've got the power law then, because it's all very well sticking a resistor in there, but what if we need one of those big fat white ones that I've just passed around and we put one of the little skinny blue ones on there? We're going to start releasing our blue smoke again, so it's probably worthwhile calculating that. So we've got the current, we know that, 20 milliamps. We've got the voltage, we know that, 3 volts. So if we do the sums, we know that we end up with a minimum of 60 milliwatts that it needs to be able to take, and then we won't be releasing the blue smoke. So that's just a sort of an example of how would you use those pieces of knowledge from the 18th century.
So what do you actually do with that?
And that's the size of the resistor you need. So you need to know how big that resistor is going to stop it's going to stop too much current flow.
Yeah, what I mean is you haven't shown where the value of which type of resistor you need from that. Don't you need to?
Oh, it needs to be 150 ohms or more is the value of the resistance, and it needs to be able to handle at least 60 milliwatts or more.
Bigger means you could. No, I was.
Yeah, so then when you go to the Amazon, you read through the specs, and it'll say, you'd say I want 150 million.
I read your ohms there as the resistance of the diode.
Oh no, yeah, the diodes are funny, they sort of don't have resistance, but do have, it's dynamic, it's always 2 volts. So if the current changes through, it means the resistance must have changed. So you calculate the resistor to limit the current.
You assume the LED's got 0 resistance with its terminal.
You
would need another resistor.
I got that when you were on that stage, and then I got to this stage, I've forgotten which bit that was referring to. So.
Okay. I'll make this slide available afterwards, and I'll drop some links in as well, so you can sort of look back through. I'm whizzing through quite quickly, just because there's the whole of electronics to cover. So. Okay, so unless anybody else has got any questions, have we covered questions, or have we not covered questions? Anybody got any questions about sort of that basic fundamental concept? No, brilliant. And unfortunately, the smokers amongst you don't get a break. So we'll move on. To part 2, electronics. So I said I'd talk about what the difference between electrics and electronics is. And the fundamental difference is electrics is passive component. So our resistor, current flows through it, but it doesn't really do anything. It responds to what's around it. So if you imagine you turn on a light with a light switch, there's nothing much going on there. There's no interaction with the world. There's no active components there. If you had a dimmer switch on your lights, if it was a resistor that's varied, it's still a passive component. If it had a bit of circuitry in there to control the voltage, it might be an active circuit. But if you imagine on your screens, and it's got a little sensor in there that sees the ambient light and turns the brightness up and down, that's got active components in there. So that's an active circuit. That's electronics. So it's responding to the signal. You've got an input in there from the light from the outside world. There's a little sensor in there, and then it turns the brightness up and down in response to that. So that's an active circuit. So electronics is active and electrics is passive. So we're going to talk about some power and signal. So there's a difference between power and signal. So we're going to sort of base it around this. I want my drone to fly. And to make it fly, I need to spin some propellers to generate some thrust. To do that, we need some motors.
Is this your one?
Yes.
It's a different video.
It's not me.
That's really good.
So we need motors. So if we're going to use motors, we best understand something a bit about motors. So we've got another beardy 18th century bloke called Maxwell. He came up with the corkscrew rule. If you run some current through a conductor, it generates a magnetic field. And if you put your right hand out, you can predict how that electric field is going to behave. Your thumb is the current, and your fingers are it's a rotational electric field. So another one, Fleming, he had left-hand rule. Says you can, is FBI, so the force is your thumb. B is the electromagnetic field, B is the symbol for that, and I is current again. So if we look at this one here, I'm going to stand so I can see it. So currents is flowing clockwise around that circuit. So if I line up my finger with the thing there, it's going clockwise. The electromagnetic field is going across, so we know that the wire is going to move upwards if we put that current through. So we can generate some force then. So we're getting closer to spinning those propellers around because we can generate some force. And if we take it a step further, we've got the similar circuit on the left-hand side. We've got force going up, and the current on the other side is going the other way. So we've got some force down. So that's going to create a rotational force. If you look at the circuit there, every 180 degrees the current reverses, so we're going to continue to generate that force in the same direction. So we've got a DC motor there. But if anybody's done Scalextrics racing, slot car racing, and you get sparks flying and you get that blue smoke smell, so that's not brilliant because that's releasing energy into the world that we don't want to do. It's not very efficient. Another thing is where we've got that contact, where we're delivering the electricity into the rotating part, those pieces can wear out. So we can do better than that. So here we've got three pieces of wire, generate 3 magnetic fields. So if we look at the top right one, if we made that south pole, which way would the middle turn? Yeah. And if we made the other two a north pole, that would help it along its way. And then if we made the top one and the right-hand one and the bottom one a south pole, we could rotate it more. And if we carried on that, we'd move the magnet around, we create rotation, but there's no contact there for the electricity. And we can generate those signals. Anybody remembers circle theorem from school? Sine wave? No. Yeah. Basically, a sine wave, if you take a circle and you plot the movement of the radius around the circle, that generates a sine wave. So if we reverse that process and inject 3 different sine waves separated by some degrees, 120 degrees, 360, 120 degrees, that would create our rotating magnetic fields. So we we can do that. We could probably write the software to do that in CSS3 to generate those 3 sine waves.
Why isn't that AC?
It's called a brushless DC motor, but it's a bit of a misnomer. It's actually a special kind of AC motor. So well done. I've lost my mouse. Okay, so if we take that whole thing and turn it inside out, inside this drive, this is the kind of motor you got. So instead of having the coils on the outside and magnet on the inside, we've got the coils on the inside and magnets on the outside. So I've got some more props here. So you've got motors, and you'll see them as they go by. They've got coils on the inside, magnets on the outside. And that's what's attached to these ones here. Those ones have been broken through abuse, whereas these ones work. So we can generate some force. We can make those propellers spin round and round and round and round. And I can actually plug a cable from my MacBook into there and make those motors spin round. But the sort of the power stage on there is 30 amps, and a sort of a USB connector's 2 amps maybe. So we've sort of got a bit of a mismatch there. I'm sure Toby wouldn't be happy, or Craig wouldn't be happy if I started pumping 30 amps through my MacBook to drive some motors. So we separate that out and drive them off the battery. So this circuit here is a power stage, and there's a whole bunch of stuff going on there. But you can see sort of 3 lines through there. We've got 3 channels. Remember, we needed 3 magnetic fields that rotate to generate that force. So you can sort of track through there, 3 lines. Left-hand side is a bit of a circuit, integrated circuit, a chip there to do some signal modification. But on the right-hand side, I sort of point. We've got pairs of gates here. So one does the pushing and one does the pulling, because if it's a sine wave, it needs to go positive and negative. So we've got a pair of gates here, got another pair of gates here, we've got another pair of gates here. And I've got some more gates as well. See if I can get these across without dropping them. So these are a bit more chunky and not suitable for drones from the past, but they're quite cool for valve amps to make a very nice sound. It's the same thing. So basically those gates are controlled like it sounds as a gate. It opens and closes a gate. So that's letting current flow through or controlling the flow of electricity, the voltage or the current based on the signal that's inputted to them. So remember we said passive circuits do nothing and active circuits do something. These are active components. So if you change the signal that's fed into them based on how they're set up, you can either change the voltage across them or the current through them. So that's how we're going to deal with our 30 amps away from the MacBook. But it does mean we can now put a small signal in and get big signal out, which is good. So we move on to another circuit. So there's a big chip in the middle that does a load of the controlling. You can't really see as well, the 3 pass through. But the input to that is pulse width modulation. Maybe means something, maybe not. It's from the olden days from radio controlled planes. They used to control servos with pulse width modulation. So basically it says that you get pulses being sent, and the wider that pulse is, the higher the number is that it generates. So we take that pulse width modulation and we jiggle it through a chip there, and out the other end comes our sine waves that we pump into our power stage. So we've managed to separate out creating the signals, generating those sine waves from actually driving the motors, so we're not going to blow up expensive electronics. And you end up with something like this. So from those 2 pieces of circuit, you end up with something like this. Ooh, a bit more props. So we've got one to look at here. Oh, that's a good one. Yeah. This one's not so good. If you look at the corners of the 2, where the gates are, so at the end there, remember I said we've got pairs of gates, we've got two at the top, 2 at the middle, 2 at the bottom. If you have a look at the gates on there, one of those sets has released the black smoke from there and not released the black smoke from my MacBook, which Toby and Craig will be happy about. So that's sort of illustrates why we separate those two out. So if we wanted one of those kind of circuits, we can either get all our 18th century beardy rich people and look at what they said about electrics and electronics and physics and maths and design that circuit. It's all reasonably straightforward given time. Or we can use what's called a reference circuit. So those two circuit diagrams I had there, they're what's called a reference circuit. So people that make chips also give you a set of basic instructions on how to use their chips, so you don't have to work it out for yourself, and just to prove that it actually does what they say it does. So you could get one of those. So if you did it from scratch, it might take you a couple of months to design a circuit. If you took one of those reference circuits, it might take you a couple of weeks to build one of those. But there is another alternative. You can go onto eBay or Amazon or Hobby King or Gearbest or TomTop or Banggood, and you can get them for a few pounds quite quickly. So that's power, but we've got some power, so we can make it go up in the air. We need to control that then, because we have external factors influencing our drone. We don't just want it to sort of go up and carry on going up. So we're going to look at a control loop, it's a PID control loop, which is sort of a classic robotics control loop. And I've got another little demo which may or may not work, but we'll see. I was hoping to show you a video of you watching me, but that's not going to work out, so you'll just have to imagine that it's being on the screen. But then if you can see there, as I rotate the drone, the camera there stays fixed in space, so that takes us back to the gun on the tank being controlled, fixed points in space. Can you see that?
Yeah.
Cool. So that's the kind of control we can have, and I'm not doing anything there. I've not got like a thing there, or Jake's not got a little remote control there to keep it stable. That's all automatic. And it's just that kind of classic robotics PID control loop. So we'll take a look at that, because that's quite cool. So there's what the control loop looks like, sort of idealised, stylized. So we've got some parts of it. You imagine you're driving along in your car, you come to a hill, you want to be doing 69 miles an hour because nobody does more than that, just in case. So you come up to a hill, your throttle's at 60%, and you come to the hill, and you don't change the throttle, what happens? Slow down. So then what do? More accelerator. And then we're going down the hill, the opposite, start speeding up, so we back off. So that's control loop. The sort of the piece of flesh and bone in the middle is the processor that processes the signals that are coming in, so you can see the speed, and you're sending out a signal to the accelerator. So the speed we want to go, so we said 69 miles an hour, that's our set point, that's the speed we want to go. So my drone now, I wanted the camera to stay fixed in space, that's my set point. Next one is the control value, which is here. And that's our throttle position. Our control value is 60%. I said the throttle was at 60%. We go 69 miles an hour on the flat. with no wind. And then we've got the process value, so we've got the output as well. So we know we want to do 69 miles an hour, we know we've got 60% throttle, and our output says we're doing 68 miles an hour, which way then we feed back into the system and generate error, process error. So if we take what we want and take away what we've got, it gives us the error. So we've got an error of 1 mile an hour. So we take that knowledge, the fact that we're 1 mile an hour out from where we want to be, and we've got the PID of a PID controller. So we've got the P is proportional to the error. That's dealing with the present. Right now we've got 1 mile an hour error, so if we had a 2 mile an hour error, we'd inject more into the system. You'd put your accelerator down harder if there was a bigger error. If you're doing 75, 80, 90, if you're doing 90 miles an hour, you'd be backing off quite hard. If you're doing 69.5 miles an hour, you might back off just a little bit. So that's proportional, that's right now. And if anybody remembers from calculus, the I is the integral, which deals with the past. So the integral is the area under a curve, so the longer the error exists, the more significant that factor becomes. And the final one, the D of PID, is the differential. So that's the difference. So the difference in time. So that's dealing with the future. So we can predict the future. We can predict the future of our car. If we're going at 69 miles an hour and the speed is dropping 1 mile an hour every second, we can predict that in 10 seconds it drops by 10 miles an hour. So we can predict the future. And that's what the D handles, is that kind of predicting what's going to be happening in the future. So if we take each piece of the puzzle in turn. So we start with proportional. We've got a seesaw there. We've got our set point. We want it to be in the middle, but it's not anymore. So now we've got an error. If we were to get a spring on the other end, the bigger the error, the more we push down on the seesaw and we stretch out that spring, it would be applying force back again. If we compress the spring, it'd be pushing back the other way. So the bigger the error, the bigger the force. So that's proportional to the error. And it wouldn't compensate for that. But we all know if we've got a spring, springs are springy. If you get a ruler and go, it would go, or something like that. Which isn't great if you're trying to control your 3D printer. If you ask Dan to print you out a Groot and you only had springs to control its position, it'd be quite a wobbly, wiggly. It might be okay. That's what you're after, but it wouldn't be what you were expecting. So the D, we've got our set point, got our error. If we add in some damping, so car suspension, you've got a spring and you've got a damper, hydraulic or gas damping. And people that aren't into cars, imagine you get some corn flour and water. Everybody done that experiment? No? Like, look. If you get a spoon into corn flour and water and move it slowly, that's all fine. Whereas if you try and move that spoon quickly, it doesn't happen. It goes stiffer. Same with suspension. So that's our derivative. And I've skipped the wrong way around because PD is quite a common control, and we'll do I last. So your car suspension is PD. You've got your spring and you've got your damping, and that will give you quite good control, but not perfect. So if I inject a signal in like that to a system, we might get that if we're under damped. And it's getting smaller and smaller and closer to what we want, but we would never actually reach what we want. And the alternative is it might, again, continually getting closer and closer, but never actually get there. Which is fine in the car. You're not really particularly bothered whether your ride height is actually where the manufacturer designed it. Again, Dan's 3D printer, you get some wonky groups coming out, but you never quite got to where you wanted to get to. So we can do better than that. So we got our set point, we got our error, and we got our pesky bird. Well, it wasn't a pesky bird, it was a big heavy weight. If it was a bird, it might, if you got a big enough spring on there, it might be enough to just get it pretty close to back where we wanted it. Big heavy weight, that's not going to happen. So what if we came up with this contraption here. So what's happening here? Tap at the top, it's dripping down, drip, 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 filling up the bucket. Because of the angle of the bucket, the water can't get back out again. So the bucket's going to fill up over time. Remember we said that the integral was dealing with the pass. So the longer that area exists, the more the bucket fills up. Eventually, we're going to level out. That's fine. Water coming in is coming back out at the same speed. Drip in, drip out, drip in, drip out. So it's going to stay level. If we went the other way, we've got more water coming out. 2 drips out, 1 drip in. So eventually that bucket's going to empty if it's like that. And it's going to come back level again and come back into equilibrium. It's not a good word for this. So that's our integral. So we've got our proportional, we've got our spring. So the more you press it or the more you stretch it, the more force it applies back in the opposite direction. We've got our damping, so we're either sort of running a spoon through our corn flour and water, or we've got our gas suspension, our slammed Peugeot 205. And we've got some integral as well, so we're dealing with past errors. So it's this system should, provided the bucket's big enough, eventually come back into equilibrium, which is what we want. So again, my camera on the drone, there's small movements, but eventually it comes back into equilibrium. Otherwise, you'd get errors. It drift off if you didn't have this in place. So what's that look like for a drone? This section here, there's a bunch of sensors. And at the top there, I can just make it out. So the left-hand column is proportional, middle column is integral, and the right-hand column is derivative. So we've got our PID control. There's lots of settings there. There's even more if you click on advanced. And I'll just click the auto, just do it for me. So that's what it looks like. So there's lots. The drone there's got 3 sets of sensors for its position, plus a GPS, plus a barometer as well for height. So if we take our PID back to software again, because we're a software company, so it's sort of good to bring it back round again. On one of our sites, we've got like the most popular pages section, and that's PI loop maybe. The more times a page has been viewed, the more its ranking goes up in the most popular pages section. And we've got a decaying average over there, so we reduce them every night, which deals with the error over time, maybe. I can't quite work out, it's a bit woolly. But I did think of another scenario. Say we've got NCT people here, someone wants some computing power, and they want that computing power to scale based on demand. So our PID control loop is perfect for that. So demand increases, your capacity increases. If I draw another little drawing, if we tune it right, and these things are a pig to tune sometimes, we'd have something like this. So we'd have one overshoot, we'd land, and that's what we call critically damped. So the system can be critically damped. I think if you're trying to sort of scale some computing power with that would be quite a nice result of sort of increases and decreases of demand. So that sort of brings it all back around again. And just to sort of look back through what we've done, we've looked at magnetism, electricity, motors, talks about separating out signal and control, and why, and you've seen why. And looked at some control. So we sort of skipped quite a lot of electronics, but we've done some quite cool stuff. We didn't get to see the video of you watching me, watching you, watching me. But has anybody got any questions on that? No.
That would do perfectly on that line, with it would drop below.
No, stay on that. So you'd have to tune it so it does that. So the K in the PID, the K is a constant. So each one, you take the error, you put it through each of the circuits, and you multiply it by constant, and you get a correction that you add them all together that gives you a signal back out again. And what you're aiming for that's called critical damping. The one before would be what your suspension would be like. It'd either be underdamped, so you sit in your car and the suspension would eventually settle, but not the same ride height before you got in there. It's a little bit lower, so that's. Whereas this one, we're aiming to get it to match, and that would then track until the signal changed again. So say demand dropped, you get another one, a little undershoot, and then it will follow. Cool. Over to you, Craig.
Brilliant. Thank you very much, Andy.